Hello everyone. In previous lecture, we have studied the fragmentation pattern and characteristics in relation to parent structure. Now, in today's lecture, I am going to discuss the fragmentation characteristics in relation to functional groups. In previous lecture, we have studied some rules of fragmentation depending upon the functional group. For example, for alkane and also for alkenes. Now, let us see the fragmentation rules of some functional groups like alcohols, aldehydes, ketones, nitro compounds, halogen compounds, etc. So, let us see in detail. In today's lecture, I am going to discuss the fragmentation characteristics relation to functional groups such as alkenes, aromatic compounds, alcohols, aromatic alcohols, phenols, aldehydes, ketones, nitro compounds, aliphatic acids, halogen compounds, ethers, and aromatic ethers. First of all, the fragmentation pattern and rules related to the functional group alkenes. The molecular ion of alkene containing one double bond tends to undergo allylic cleavage, that is, at the beta bond without the double bond, and it gives the resonance structure. The molecular ion peak in the spectra of unsaturated compounds is more intense than the corresponding saturated analogues. The reason is that the better resonance stabilization of the charge on the cation, which is formed by the removal of one of the pi electrons. As we know, in alkanes, only the carbon-carbon single bond and each and every carbon-carbon bond undergo the cleavage, and due to that there is a formation of number of fragments, or in the mass spectrum of the alkane we get the cluster of the peaks due to the cleavage of carbon-carbon bonds. Whereas in unsaturated compound, if you observe the mass spectrum, here the spectra of unsaturated compound is more intense as compared to the saturated analogues, and the reason is nothing but the stabilization, resonance stabilization of the charge on the cation, which is formed by the removal of one of the pi electrons. The relative abundance of the molecular ion peak decreases with increase in molecular mass. The cyclic olefin also shows the group of peaks which are 14 mass units apart. The general mode of fragmentation is the allylic cleavage, and the fragments formed by McLafferty rearrangement are also more intense. Already we have studied about McLafferty rearrangement. There is a migration of hydrogen atom, intramolecular migration, or the intramolecular rearrangement leads to the formation of a number of fragments. So here the example is taken as 120. Also this hydrogen atom, it shows the migration and we get the formation of a molecular ion having the mass to charge ratio 42. So in general, for the alkenes, the molecular ion of the alkene which having the double bond, it tends to undergo allylic cleavage. That is, allylic cleavage is nothing but at the beta bond without the double bond, and it gives the resonance stabilization. Hence, the peak observed for unsaturated compound is more intense. Now, if we observe the cycloalkenes, cycloalkenes usually show a distinct molecular ion peak. A unique mode of cleavage is a type of retro-Diels-Alder reaction, and the fragmentation mode involves the cleavage of two bonds of a cyclic system, resulting in the formation of two stable unsaturated fragments in which two new bonds are formed. Again, in previous lecture, we have studied about retro-Diels-Alder reaction. For example, cyclohexene undergo the retro-Diels-Alder reaction, and due to that cleavage of this carbon-carbon double bond, we get the formation of a such a type of the fragment. Here CH2 double bond CH2, CH2 double bond CH, CH double bond CH2, having the mass to charge ratio 55. So in the cycloalkenes, we get the distinct molecular ion peak, and it is due to the cleavage by considering the type of retro-Diels-Alder reaction. So in retro-Diels-Alder reaction, there is a formation of a diene and dienophile. Here the fragmentation mode involves the cleavage of two bonds of a cyclic system that results in the formation of two stable unsaturated fragments in which two new bonds are formed. So these are two unsaturated fragments which are formed due to the formation of two new bonds. So that is overall about the fragmentation of alkenes and the fragmentation observed in cycloalkenes. Now the next functional group, aromatic compounds. In aromatic compounds, the molecular ion peak as compared to the alkanes and the alkenes containing same number of carbon atoms, the molecular ion peak is prominent. This is as a result of the stabilizing effect of the ring. Due to the presence of ring, that stability is obtained, and hence the molecular ion peak is prominent in aromatic compounds as compared to alkanes and as compared to alkenes containing the same number of carbon atoms. In these compounds, M plus 1 and M plus 2 peaks are also noticed, and it is due to the carbon 13. If the aromatic ring is substituted by an alkyl groups, a prominent peak is formed at M by Z 91. Here, the benzyl group, that is C6H5CH2 cation, it formed and it rearranges to form the propylium cation C7H7 plus. And this may eliminate a neutral acetylene molecule to give a peak at mass to charge ratio 65. So if there is a presence of an alkyl group which is attached to the ring, to the aromatic ring, then due to the presence of alkyl group, the prominent peak is formed at M by Z 91, and further this benzyl cation rearranges to propylium cation C7H7 plus, and here the formation of a peak, molecular ion peak at M by Z 90. So this may eliminate a neutral acetylene molecule to give the peak at mass to charge ratio 65. Now the next example, if we consider for ethyl benzene, that is also the aromatic ring is present here. So what happens in the ethyl benzene? Mass to charge ratio is 82. Alkyl group is present at this position. So what happens? There is a removal of this alkyl group or the alkyl substituent. So due to the elimination of this alkyl substituent, formation of such a type of the benzyl cation, and the benzyl cation, it shows the peak at M by Z 91. Further, this M by Z rearranges, this benzyl cation rearranges to form propylium cation, and there is the formation of a stable propylium cation. So like that it is observed in the aromatic compounds. Now the next functional group is alcohol. The molecular ion peak of primary and secondary alcohol is usually of low abundance, and it is not detected in tertiary alcohols. Then the fragmentation modes in alcohols also depends upon the fact whether it is of primary, secondary or tertiary alcohol, depending upon the nature of the functional group which is attached, OH group which is attached to the side chain. So as it is primary alcohol, secondary alcohol or tertiary alcohol, depending upon that the fragmentation modes are also variable. The fragmentation of carbon-carbon bond adjacent to oxygen atom is the preferred fragmentation mode. That means if the OH group is attached to the adjacent carbon-carbon single bond, then there will be the alpha cleavage. There is a cleavage, that is alpha cleavage occurs, and it is more preferable. Then primary alcohols, it shows the peak at M by Z 18. So M18 peak is observed for the alcohol, especially for primary alcohols, corresponding to the loss of water. As we have already studied, there is the loss of neutral stable molecules like H2O, CO2, CO, N2, like that. So if the primary alcohol is there, there is a loss of H2O molecule, and due to that, the peak is observed at M by Z 18. If we observe the long chain members, that may show the peak corresponding to successive loss of hydrogen radicals at M1, M2 and at M3. So long chain members also show the peak due to the loss of hydrogen radicals. The CH2 double bond OH is the most significant peak in the spectra of primary alcohols. Also, there is a formation of such a type of the fragment CH2 double bond OH, and due to that the peak is observed for primary alcohols. It is also most significant peak. Then for secondary alcohols, there is a cleavage, and due to the cleavage, we get the peaks at RCH double bond OH at M by Z 45, 59 and 73. So the prominent peak is observed for secondary alcohol due to the cleavage, and there is a formation of such a type of the fragment RCH double bond OH, which shows the peak at 45, 59 and 73. So it is observed in case of secondary alcohols. So in primary alcohols, the peak observed due to the loss of water molecule at 18, M by Z 18, and in the secondary alcohols, cleavage is observed due to the prominent peak RCH double bond OH at M by Z 45, 59 and 73. Now the aromatic alcohols. In case of aromatic alcohols, the relative abundance of the parent ion of aromatic alcohols is larger. Some of the fragment modes of benzyl alcohol are loss of 1, 2 or 3 hydrogen atoms. Some of the fragment modes of benzyl alcohol are loss of 1, 2 or 3 hydrogen atoms. Here also M plus H fragment of benzyl alcohol rearranges to form hydroxytroponium ion. The OH group in the benzyl positions fragments in a way which favors the charge retention on the aryl group. Similar to aromatic compounds, here also the formation of a troponium ion, which is a stable ion. So some of the fragment modes of benzyl alcohol are loss of 1, 2 or 3 hydrogen atoms. There is a formation of a benzyl alcohol. Further, benzyl alcohol rearranges to form hydroxytroponium ion. Then the next functional group, phenols. The molecular peak observed in the phenols, it is very intense, and the peak due to the loss of hydrogen radical M plus H is small. Here the fragment ion due to the loss of carbon monoxide is very significant in case of phenols. Cresols form very intense peak due to the formation of hydroxytroponium ion. So here also the alkyl group is substituted at the benzene ring. Due to that, there is a formation of a benzyl cation. Further, benzyl cation rearranges to form hydroxytroponium ion, and due to the formation of hydroxytroponium ion, the peak observed due to the cresols, it is very intense. And in case of phenols, the molecular ion peak is intense. Here there is the loss of hydrogen radical and also the loss of carbon monoxide. Next functional group, aldehydes. The molecular ion peak of aliphatic aldehyde is weak as compared to aromatic aldehydes. Then the aromatic aldehyde shows moderate intense peak. RCH double bond O plus, that shows the formation of such a type of the fragment R3 triple bond O plus H plus. So here the characteristics of aldehyde, especially the aromatic aldehyde, there is loss of alpha hydrogen. Here the loss of alpha hydrogen take place, and due to that the aromatic aldehyde shows the moderate intense peak, loss of alpha hydrogen. in case of aromatic aldehydes. Second common feature of aliphatic aldehyde is beta cleavage. For example, aldehyde with CH2CHO end group give rise to the characteristic M plus 43 peak M by Z 43 peak. So we should remember the molecular ion peak of aliphatic aldehyde is weak as compared to aromatic aldehydes. In aliphatic aldehydes there is a beta cleavage, whereas in aromatic aldehyde there is a alpha cleavage. There is a loss of alpha hydrogen, and due to the loss of alpha hydrogen, the aromatic aldehydes it shows the peak, intense peak, moderate intense peak. And if the aldehyde having the alkyl substituent CH2CHO group, ending group, that give rise to the characteristic peak at M by Z 43. Now, what is about ketone? In case of ketones, the molecular ion peaks are intense as compared to aldehyde. Most of the abundant ions in the mass spectra of ketones can be accounted by alpha cleavage and also by the McLafferty rearrangement, which is intramolecular rearrangement. So due to the loss of alpha substituent, alpha cleavage, and due to the migration of hydrogen intramolecular rearrangement, the peaks observed in case of ketones are more intense as compared to aldehydes. Next one, nitro compounds. Aliphatic nitro compounds fragment by loss of NO2 group to give the strong carbonium ion. So here if we take the example of nitro compound RNO2 plus, further the NO2 group will be removed and we get the substituent or the fragment R plus. So here due to the loss of NO2 group, the formation of a strong carbocation occurs and we can observe the peak. And also in some cases the McLafferty rearrangement occurs, but such type of the peaks are weak. In case of nitrides, there is the beta cleavage, and due to the beta cleavage also the peaks can be observed. So we should remember in case of aliphatic nitro compounds, there is only the loss of NO2 group and formation of stronger carbonium ion. In some cases, the McLafferty rearrangement also occur, but the peak observed due to the McLafferty rearrangement, it is weak. Next functional group, aliphatic acids. In case of aliphatic acids, the molecular ion peak is less intense as compared to that of aromatic acids. Here, the carboxyl group is directly eliminated by alpha cleavage and a signal is formed at M by Z 45. So, carboxyl group is removed directly by alpha cleavage and the signal is obtained at M by Z 45. But if we compare the aliphatic acids, that shows the less intense peak as compared to aromatic acids. If alpha carbon atom is not substituted in aliphatic acids containing a gamma hydrogen atom, McLafferty rearrangement ion is formed at M by Z 60. It is also often the base peak observed in case of aliphatic acids. In short chain acids, MOH and MCOOH peaks are prominent. In next lectures, we will also discuss some examples of such a functional groups like acids, then aromatic compounds, alkenes, nitro compounds like that. Now the next functional group, halogen compounds. A compound with one chlorine atom that shows the peak at M plus 2, which is 1/3, and the intensity of the molecular ion peak due to the presence of molecular ion containing chlorine isotope Cl37. In a mono-bromo derivative, the M plus 2 peak is almost of equal intensity to the molecular ion, and it is also due to the presence of molecular ion containing Br isotope, Br81 isotope. If the fluorine and iodine is present, that fluorine and iodine being monoisotopic that do not give this type of the pattern, whereas only the chlorine isotope and bromine isotope it can show the peak, that may be M+2 peak which is observed, and there is the equal intensity of peak M+2 due to the chlorine isotope or due to bromine isotope, whereas fluorine and iodine that will be monoisotopic that do not give the such a type of the peak. Then aliphatic chlorine compounds fragment mainly by the loss of HCl to give the peak at M36 and M38. HCl peak can also be seen at M by Z 36 and M by Z 38. Especially for aliphatic chlorine compounds, there is a loss of HCl group, and due to the loss of HCl that show the peak at M by Z 36 and M by Z 38. The relative abundance of the molecular ion, it also decreases with increase in the chain length and increases in the branching. So if we observe the chlorine isotope or the bromine isotope, due to the presence of a chlorine atom and due to the presence of bromine, the peak is observed at M+2, but in case of fluorine and iodine, that will be not observed, and only the reason is that fluorine and iodine it is monoisotopic, so that do not show such a type of the pattern or such a peaks. So it is observed in case of halogen compounds, and the relative abundance of the molecular ion also decreases with increase in the chain length and increase in the branching. Now the next one, that are ethers. In case of aliphatic ethers, due to the facile fragmentation that exhibit a weak molecular ion peak, because the resultant ion is highly stabilized by resonance. The major fragmentation modes which are observed in case of ethers, that are due to the cleavage by alpha and beta bonds. So the alpha and beta cleavages occurs due to these alpha and beta cleavages. The fragmentation is observed in ethers. If we consider the alpha cleavage, the cleavage of a bond alpha to oxygen occurs, and the positive charge being retained on the carbon rather than on the oxygen. If we observe the beta cleavage, a heteroatom induces the cleavage at a bond beta to it, and such a cleavage favors the loss of larger group as a radical. The ion undergoes further fragmentation to give the series of ions. For example, the ether, diethyl ether. So in case of ether, there may be the fragmentation modes, that are alpha and beta cleavages. Where the alpha cleavage occurs, here the cleavage of a bond alpha to oxygen occurs, and in that the positive charge being retained on the carbon rather than on oxygen. So positive charge is present on the carbon atom instead of the heteroatom like oxygen. But if the beta cleavage occurs, a heteroatom induces the cleavage at a bond beta to it. Such a cleavage favors the loss of larger group as a radical, and the ion undergoes further fragmentation to give the series of ions, series of carbocations, like that. Then for aromatic ethers, the molecular ion peak of aromatic ether is prominent in that primary cleavage occurs at the bond beta to the ring, and first form ions can decompose further. So there is a beta cleavage occurs in case of aromatic ethers, and due to that the molecular ion peak of aromatic ether is prominent as compared to aliphatic ethers. Aliphatic ethers undergo the facile fragmentation, and they exhibit a weak molecular ion peak because the resultant ion is highly stabilized by resonance, whereas in molecular ion peak of aromatic ether, that is more prominent, and the cleavage occurs by beta bond, beta to the ring, and again there is a decomposition of the first ion form. So in today's lecture, we have discussed some fragmentation pattern of functional groups. Now in next lecture, we will discuss the fragmentation pattern of each functional group with some examples. Thank you.